So before talking about the maximizing margin, we have to understand how to measure the distance between the point and line. Okay, so first, so distance between the x naught and this line is this one. So when we have x naught here and when we have one line here, then we want this distance between this point and the line, and that is this one. Okay, so we are going to prove that one. So let xa and xb on the same line. So we have 2 points here. Then, since these 2 points are on the same line, so this one and this one should be the same. Okay, then we can rearrange the term. So by this, w is orthogonal to the line. Okay, so we have w like this. So if we extend, then we have orthogonal kind of a vector to this line. Okay, now let's check the distance from the origin to the parallel line to this one, passing this one. So I'm talking about this line. So this line is parallel to this line, but it is passing x naught. Okay, then you know how to calculate the distance. So this is what we can get. Okay, so we actually normalize this w by this, and then we calculate the inner product between this vector and this point. And then this one is actually the magnitude of this vector from origin to this line. Okay, so this is what we have. And then what we are interested in is this distance. So we have to calculate this one, because since we have this one, so now we have to calculate this one. Okay, then the distance from the origin to the line, let's say we have xa on the line, so we can get this one. And then, as you know, this one is this line. So with this equation, this one is actually this one. Okay. Then the distance between x naught and this line is this one minus this one. So this is what we have. This is exactly the same as this one. Okay, so now we can calculate the distance between a point and a line. Okay. Now let's calculate the margin between two classes. Okay, so we have one line and another line. So now the margin between the two classes is this one. And then that margin is 2 over the norm of w. That's the margin. And then let's prove. Since we assume a linear separable data set, we can draw two lines like this. So this one corresponds to this one, and this one corresponds to this one. So this one is the closest line touching any kind of point in this class. And this line is the furthest line from the origin while touching some kind of points in this class. Okay. And then the distance from the origin to this line is this one. Let's say there is one point here, and then if that is x naught, and then this is the distance. Since this is the line, so with this one, actually this is the distance. So this is what we have. Okay. And then likewise, the distance from the origin to this line is this one. So this one is this one. And then the margin is this one minus this one. Okay, then the 2 over the norm of w. Okay, so in this slide, you can see that the maximizing margin is actually minimizing w, the norm of w. Okay, so now we want to minimize w. That's what we want. Okay, so now we are going to formulate the problem with all the knowledge from the previous slide. First, we want to minimize this one. So this constant is just when we take a derivative, then it will cancel. So we just put this constant, but basically we want to minimize this one. Okay, but there is a constraint here. So when we apply these samples to this equation, then it should be greater than or equal to 1. Okay, because this one is the smallest one. Okay, and then in this class, yi is 1. It is a label. In this class, this one should be less than or equal to minus 1. Okay, so this one is minus 1, and these ones are less than minus 1. And then yi is minus 1. So if we multiply this one and the yi, or this one and the yi, it should be greater than or equal to 1 for all I. Okay, so no matter what kind of point, from this class or from this class, it doesn't matter, since we have a class information here. So if we multiply this label and this equation, then it should be greater than or equal to 1. Okay, so to solve this problem, we need the Lagrangian optimization techniques like KKT conditions. So let's talk about KKT conditions in general. So given a convex optimization problem, so minimizing this is objective function, and then there are some constraints, inequality constraint and equality constraint. So in SVM problems, we don't have equality constraint, but in general, we can have inequality and equality constraints. And then the problem can form a generalized Lagrangian function like this. Okay, and these are Lagrangian multipliers. And then there is a theorem, the first order necessary condition theorem. So if W star is a local solution of f of W satisfying all the constraints, then there are alpha star and the beta star such that the followings are satisfied at this point. So look at this one. This is our parameter, and when we take a derivative, it should be 0. Okay, and then this one is our constraint. Okay, and then this one is another constraint, and the Lagrangian multiplier should be positive, or it could be 0. And then this one is especially important because these are KKT conditions, but this one is actually KKT complementary condition. Okay, so we're gonna use this one many times. But anyway, what this equation says is that when we have an inequality constraint, then this Lagrangian multiplier or this equation, either this one or that one should be 0. And actually only one of either this one or this one should be 0. That's what KKT conditions say. And then we're going to use that KKT conditions in the SVM problems. Okay, so when we use a Lagrangian function for the SVM problem, okay, so we have objective function and we have a constraint, and then we have Lagrangian multipliers. And then we can rearrange this term. So we have here, and we have here, and we have this one. Okay, so this one is a Lagrangian primal problem. So we just formulated the objective function and the constraint with the Lagrangian function. Okay, so it's primal problem. And then using the KKT conditions on the primal problem, so we can take a derivative with the W, and then also we have a bias, so we can take a derivative with respect to the bias, and they should be 0. So by this one, we can have this one. Okay, and then if we calculate the W transpose W to calculate the norm of W, then it is actually this one. And then by this one is 0. So this term will be 0. Okay, and then now these two terms will be this one, because this one can be rewritten by this one, and then this one also, alpha I, yi, and if we use this W, like summation alpha j, yj, xj, and xi, and it's basically the same as this one. So since we have 1 over 2 and this one is minus 1, so we have minus 1 over 2. Okay, and then this term goes to here. So this is Lagrangian dual problem. Okay, so look at this one. This function depends on alpha, not w, not b. Originally, w and b, these are the parameters in the primal problem. But in the Lagrangian dual problem, now we have alpha. It was a Lagrangian multiplier here, but now it is our parameter, not the wb. Okay, and then as you can see here, we're going to use a kernel trick for this one later. Okay, so just to keep this in mind. So in this equation, the x, they have the inner product form, so xi and xj. So we don't have xi separately. So when we have xi, then always we have inner product form here. That's one thing that we're going to use for the kernel trick. So now, by the KKT complementary condition, this should be 0. And only one of either alpha I or this one should be 0. So when the alpha I is non-zero, so if it is positive, then it should be 0. So which means only when the alpha I is positive, then do we have the points on this line or this line. When the alpha I is positive, the samples are on these two boundary lines. Okay, so we call them support vectors. They actually support the classification boundaries. They supported the boundaries, so we call them support vectors. So in this example, we have 3 support vectors. Only they have a positive alpha I, and then for all the other points, alpha I is 0, which means this one is positive. This one, W transpose Xi plus B is greater than 1. Okay, so now the ultimate separating hyperplane, this one is this one. We don't actually solve these equations by ourselves. We're going to use some tools later. So if we solve this Lagrangian dual problem, then we have alpha and the y and x, they are the data samples we already have. So now W star is given by this one. And I goes from 1 to n, but actually we can consider just support vectors. Okay, so in this case we have only 3 support vectors in this example, so it's a simple. And then B star is obtained by this one. So we already have yi, xi, and w star, and then bi can be obtained by this one. So actually, by rearranging these terms, b is given by this equation. So this is the solution of SVM when the problem is the dataset is linearly separable.